Java 21 has introduced a groundbreaking feature, virtual threads. This marks a major shift in how developers approach concurrency in Java applications. By breaking the traditional one mapping between application threads and OS threads, virtual threads allow for lightweight, scalable concurrency. In this video, we'll explore what virtual threads are, how they work, and why they're a game changer for handling millions of concurrent tasks efficiently. Let's start by understanding the basics of concurrency and why virtual threads matter. Before diving deeper, it's crucial to distinguish between CPU-bound and I/O-bound operations. CPU-bound tasks are those where the CPU is the bottleneck, actively performing computations. Examples include mathematical calculations, data processing, and encryption. On the other hand, I/O-bound tasks spend most of their time waiting for external resources, such as database queries or network requests. Understanding this difference helps us see why traditional threads often waste resources, especially during I/O waits. Let's look at a CPU-bound operation in Java. When a thread is calculating something like the Fibonacci sequence, it constantly uses CPU cycles without waiting or blocking. This means performance is limited by CPU speed and the number of cores. Adding more threads than CPU cores doesn't help. It actually causes contention and slows things down. For CPU-bound tasks, threads are always busy, and there's no opportunity to free up resources. Now consider an I/O-bound operation. Here, a thread spends most of its time waiting for external resources, such as database queries or HTTP requests. While the thread is blocked, the CPU sits idle, and valuable resources are held without doing useful work. This is where traditional threads waste memory and processing power, especially when scaled to thousands of requests. Virtual threads address this inefficiency by freeing up resources during wait periods. In traditional Java, platform threads are mapped directly to OS threads. When a platform thread waits for I/O, it occupies about 1 MB of stacked memory, even though the CPU isn't doing anything. This means the OS thread is blocked and unavailable for other work, leading to massive resource waste when handling thousands of concurrent requests. Memory constraints and OS thread limits make it impossible to scale efficiently with platform threads. Each platform thread in Java reserves a significant amount of stacked memory up front, typically around 1 MB. This reservation happens whether the thread uses the memory or not. If you try to create 10,000 platform threads, you'll need about 10 GB of memory just for stacks. This creates a hard limit on scalability, making it impractical for applications that need to handle massive concurrency. Platform threads have a strict one-one relationship with OS threads. Each Java thread maps to exactly one OS thread, which is an expensive resource managed by the kernel. Context switching between OS threads involves kernel-level operations and is limited by OS thread limits, usually in the thousands. This mapping restricts scalability and increases resource consumption, especially in high concurrency scenarios. Virtual threads are managed by the JVM and run on a pool of platform threads called carrier threads. The JVM uses a fork join pool as the default scheduler, with one carrier thread per CPU core. Creating a virtual thread is cheap, and the JVM handles scheduling and execution, allowing millions of virtual threads to run on a handful of carrier threads. This model is the foundation of lightweight concurrency in Java 21. The magic of virtual threads lies in their mount and unmount mechanism. When a virtual thread needs to execute, the JVM scheduler assigns it to an available carrier thread. The virtual thread's execution state is loaded onto the carrier thread stack. When the virtual thread performs a blocking operation, it unmounts, and the JVM takes a snapshot of its stack, storing it in heap memory. The carrier thread is then free to run another virtual thread, maximizing resource utilization. When a virtual thread blocks, the JVM captures its current call stack and stores it as a regular Java object in the heap. The carrier thread is immediately released, and all local variables, method frames, and execution context are preserved. This allows virtual threads to pause and resume seamlessly, even on different carrier threads, without losing any data or state. What happens when all carrier threads are busy? Virtual threads ready to run are queued by the scheduler. The scheduler uses FIFO scheduling, ensuring no blocking occurs. As soon as a carrier thread becomes available, the next virtual thread from the queue is assigned. This efficient queuing and scheduling mechanism ensures high throughput and minimal resource waste, especially for I/O-bound operations. Virtual threads are stored in different memory locations depending on their state. When unmounted, their stack snapshots are stored in heap memory as Java objects. The thread object and associated metadata also reside in the heap. During execution, the virtual thread's active stack frames use the carrier thread stack, which is typically much smaller than platform threads. This dynamic memory management is key to their efficiency. When a virtual thread completes its job, it unmounts from its carrier thread. Thread local variables are cleared, and the virtual thread object becomes eligible for garbage collection. Unlike platform threads, virtual threads are not pooled or reused. The carrier thread is immediately available for other virtual threads, ensuring continuous, efficient task handling. Virtual threads are lightweight for several reasons. They don't create OS threads, avoiding kernel-level system calls and context switching. Their initial stack size can be as small as a few kilobytes, growing dynamically as needed. Memory is allocated on demand, with no upfront reservation of large stack space. Creation and scheduling happen entirely in user space, making them extremely efficient. The JVM can manage millions of virtual threads on just a handful of carrier threads. For example, creating 1 million virtual threads only requires a small memory footprint for each thread. The scheduler assigns virtual threads to available carrier threads, and when a virtual thread blocks, the carrier thread immediately picks up the next task. This architecture allows for massive scalability with minimal resource usage. Let's compare memory usage. 8 carrier threads use about 8 MB for platform thread stacks. 1 million virtual threads use around 1 GB for their data. In contrast, 1 million platform threads would require about 1 TB of memory. This dramatic reduction in memory usage is a key advantage of virtual threads, enabling applications to scale far beyond traditional limits. Here's a practical example. Using Executor's new virtual thread per task executor, you can submit 1 million tasks, each simulating an I/O operation. The executor waits for all tasks to complete, efficiently recycling carrier threads during I/O waits. This demonstrates how virtual threads handle massive concurrency with ease, making them ideal for high-load applications. When a virtual thread is allocated to a different carrier thread after unmounting, its stack snapshot is restored from the heap. Execution resumes from where it left off, and all local variables and state are preserved. This transparent migration ensures that virtual threads can move between carrier threads without any data loss or disruption. Virtual threads don't have affinity to specific carrier threads. Their migration between carrier threads is completely transparent to the code. Thread local variables stay with the virtual thread, not the carrier. This flexibility allows the JVM to optimize scheduling and resource utilization, further enhancing performance. Virtual threads are a JVM-level abstraction. The operating system has no knowledge of virtual threads, it only sees platform threads. Application code interacts with virtual threads, which are managed by the JVM, then carrier threads, and finally platform threads. This separation allows for user space scheduling, fast context switching, and platform independence. JVM-level management brings several benefits. Scheduling happens in user space, with no kernel involvement. Context switching between virtual threads is just a method call, making it extremely fast. Virtual threads work the same across different operating systems, and the JVM can optimize scheduling based on application behavior, ensuring maximum efficiency. Virtual threads can become pinned to their carrier thread in certain situations, such as executing inside a synchronized block or native methods. When pinned, the virtual thread won't unmount, reducing efficiency. The solution is to use reentrant lock instead of synchronized, allowing virtual threads to unmount and freeing carrier threads for other tasks. Don't pool virtual threads. They're designed to be created per task. Pooling virtual threads defeats their purpose and reduces efficiency. Instead, use Executor's new virtual thread per task executor to create a new virtual thread for each task. This approach maximizes concurrency and resource utilization. Virtual threads work beautifully with structured concurrency. Using structured task scope, you can fork multiple tasks, wait for them to complete, and handle failures gracefully. This pattern ensures that all concurrent tasks are managed within a defined scope, improving code clarity and reliability. Virtual threads integrate seamlessly with Java's monitoring tools. Thread dumps show virtual threads, JFR events track their activity, and JMX beans expose metrics. This observability makes it easy to monitor, debug, and optimize applications using virtual threads, ensuring robust performance. Virtual threads excel at I/O-bound operations, high concurrency scenarios, and blocking tasks like sleep, network, or file I/O. However, they struggle with CPU-intensive tasks, code with heavy use of synchronized blocks, and extremely short-lived tasks due to scheduling overhead. Understanding these characteristics helps you choose the right thread model for your application. Traditional web servers using platform threads waste resources during I/O waits. For example, handling an HTTP request involves only a few milliseconds of CPU work, but the thread holds 1 MB of stacked memory for the entire duration, mostly idle. With 200 threads, that's 200 MB of memory used inefficiently. Virtual threads solve this by freeing carrier threads during I/O waits. With virtual threads, the same operation is handled much more efficiently. When a thread receives a request, it mounts on a carrier thread. During database or API calls, it unmounts, freeing the carrier thread for other tasks. Carrier threads are only occupied during actual CPU work, allowing thousands of concurrent I/O operations with minimal memory usage. Let's simulate a real-world scenario. Processing 10,000 I/O-bound requests with platform threads would require batch processing and significant memory. With virtual threads, all requests start immediately, limited only by carrier threads. Carrier threads are recycled during I/O waits, completing tasks much faster and using far less memory. Tracing the workflow of a virtual thread during I/O operations reveals its efficiency. The thread mounts on a carrier thread for actual work, unmounts during I/O waits, and remounts when ready to continue. Carrier threads are constantly available for other tasks, and virtual threads can switch between carriers without losing state. This workflow eliminates wasted resources and maximizes throughput. Comparing throughput, a platform thread pool with 200 threads handles about 1,333 requests per second, while virtual threads with 8 carrier threads handle around 4,000 requests per second. This is a threefold improvement with 25 times less memory usage, demonstrating the power of virtual threads in high concurrency scenarios. For CPU-bound operations, virtual threads offer no benefit over platform threads. Since there's no I/O to wait for, the virtual thread stays mounted on the carrier thread, occupying it continuously. This limits concurrency to the number of CPU cores, and scheduling overhead can even make things slightly worse. For CPU-intensive tasks, platform threads or parallel streams are better choices. Virtual threads are ideal for REST API servers, microservices with external calls, database-heavy applications, file processing pipelines, WebSocket servers, and any scenario with lots of waiting or blocking. For CPU-intensive computations, real-time systems, or code with heavy synchronized blocks, platform threads are preferable. Virtual threads truly shine in applications with mixed workloads. For example, handling 50,000 concurrent user requests involving authentication, data fetching, and API calls can be efficiently managed with just a few carrier threads. Platform threads would require massive memory or batch processing, but virtual threads handle everything smoothly and efficiently. Virtual threads implement the same thread API as platform threads. You can use all standard thread methods, such as getName, sleep, and interrupted. This backward compatibility makes it easy to adopt virtual threads in existing Java applications without major code changes. You can configure the carrier thread pool in Java 21. Set the number of carrier threads and their name prefix using system properties. This flexibility allows you to optimize carrier thread usage based on your application's needs and hardware capabilities. Since virtual thread stacks live in heap memory, garbage collection pressure can increase with millions of virtual threads. It's important to monitor heap usage and GC behavior and use appropriate heap size settings to ensure smooth performance. Proper monitoring and tuning are essential for large-scale applications. Debugging virtual threads is straightforward. Stack traces include carrier thread information, and traditional thread dumps show both virtual and platform threads. IDE debuggers are being updated for better virtual thread support, making it easier to diagnose issues and optimize performance. Get the most out of virtual threads, use them for I/O-bound tasks, avoid synchronized blocks, and don't pool virtual threads. Monitor pinning events using JFR, designed for blocking operations, test with realistic workloads, and keep carrier threads proportional to CPU cores. Following these best practices ensures optimal performance and scalability. Virtual threads represent a paradigm shift in Java concurrency. By decoupling application threads from OS threads and using clever mounting and unmounting mechanisms with heap-stored stack snapshots, Java 21 enables applications to handle millions of concurrent tasks with minimal resource overhead. The OS remains blissfully unaware, and developers can write simple, scalable code. Let's recap the key insights. Virtual threads are cheap because they're JVM managed and use minimal memory. Mounting and unmounting with stack snapshots enables efficient carrier thread utilization. Millions of virtual threads can run on a handful of platform threads, and blocking operations are handled without wasting resources. This makes Java 21 concurrency both powerful and efficient. By embracing virtual threads, developers can write simple, blocking-style code that scales to millions of concurrent operations. This approach combines the best of both worlds, easy-to-understand code and high scalability. Virtual threads simplify concurrency management, making Java applications more robust and performant. Virtual threads pave the way for the future of Java concurrency. As applications grow in complexity and scale, the ability to handle millions of concurrent tasks efficiently becomes essential. Java 21's virtual threads provide the tools needed to meet these demands, ensuring that Java remains a top choice for modern, scalable applications. In summary, virtual threads in Java 21 revolutionize concurrency by enabling lightweight, scalable task management. They solve the resource waste problem of platform threads, allow for millions of concurrent operations, and integrate seamlessly with existing Java APIs and tools. Developers should leverage virtual threads for I/O-bound workloads and follow best practices for optimal results. Thank you for joining this deep dive into virtual threads in Java 21. We've covered the fundamentals, architecture, performance, and best practices. As you explore Java's new concurrency model, remember to use virtual threads for scalable, efficient applications. Stay tuned for more insights and innovations in Java programming.